Hello, everyone. Welcome to, I don't know, is this on? It is on. Okay. Welcome to the Cryosphere Pavilion. Yesterday, I heard someone walking by and they said, oh, the Cryosphere Pavilion, that's just a load of science. So, welcome to a load of science, everyone. Everyone here, and also to everyone watching online, and those watching at the Cryosphere Pavilion hubs in Stockholm and Geneva. Our first speaker in this session is going to be Maxence from the Vrije Universiteit of Amsterdam.
Hello everyone. As Hélène presented me, I'm Maxence Menton from the Vrihe Universiteit of Amsterdam. Today I would like to share some experiences I had during my start of career, sort of, and give insight from fieldwork I had the opportunity to do in Greenland, and explain why my PhD topic is really important for the society as well. So, just as a reminder, the mountain glaciers has the potential to rise the sea level rise of 0.3 meters, but mostly the ice sheets can rise the sea level of 7 meters for the Greenland ice sheet, and the Antarctica of 58 meters. But still, I would like to mention that the mountain glaciers has a huge impact in terms of freshwater resources. So this doesn't mean that we should neglect them. So I would like to start with the Greenland ice sheets. So here you see the evolution of the Greenland ice sheet mass balance over the years, over the last 2 decades. What you can see is that every year, without exception, it's melting more than its accumulating mass. I would like to emphasize the year 2012 and the year 2019, which are records of melt during the last 2 decades. On the map, you can see where the changes in the mass are the biggest. So, just to reminder you, like the 2012 and 2019s are here, and I will show you my fieldwork during the year 2019. So I was on the field with Jason Box, Masashi Niwano, and Maurice Van Tigelen. Over here in the southern tip of Greenland. So what we do there? We basically drill poles. Come one year, measure how much it's over the ice. Come the next year and measure how much over the ice it's still remaining. So here you see that the pole is very high, which means that the previous year, during this year, it melted a lot. To make you feel a little bit this experience of how much it melted, here is how much it was above the ice before. Oh, all right, it doesn't work, but I will show you on the screen how much was above the ice before. So only this part was above the ice. So you have to imagine all the ice around where we are standing here is melted away during this year. So it's about 10 meters high, and you have to multiply that by the whole surface. It's gigantic. So here you see Jason and Maurice, who are measuring how much the pole is above the ice. And I am just behind drilling for preparing the next pole. So why this year was a record, almost the record was 2012. It's mostly because we had 2 heat waves which went through Europe, where we had all-time record high temperatures in Belgium, in France, in Netherlands, and many other countries of Europe. But these heat waves didn't stay in Europe. They crossed the Atlantic Oceans and reached the Greenland ice sheets, which trigger massive melt this year. So to give you a little bit more insight of what is happening there, so the melt from the surface um, is flowing through the ice. So here is what we call a moulin. So you see the ice turning into water and flowing until finding a hole where it will go through the ice. And these are um, important processes because they are emphasizing the sliding of the ice. So it's accelerating the melt and the discharge of the Greenland ice sheet. Here is another picture on the edge between the ice and the ocean. And there are, I think, many different things that we can look at on this picture. The first one, which was very striking for me when I was there, because I was not expecting that, is that actually the ice is dark. And this is something we are seeing more and more, and not only in Greenland, but also in the mountain glaciers and also in Antarctica now. So that was really shocking for me when I was there. I was expecting like the moon, like very white landscapes, or like the snow, fresh snow, very high albedo values, and it was actually mostly dark. Those are primarily algae developing because the temperature is warm enough to that so that they can actually develop themselves, and so you have the albedo feedbacks taking place here. The other thing is this part of the glaciers were just collapsed before even reaching the ocean, and our hypothesis is that it's actually what we saw before. It was a moulin, and so sort of so much water was under that it's just collapsed by itself. And finally, you can see on the last mark that's where the glacier was about 10 years ago, and you can see with the scale with Morris here that it's actually very far, and it's melting away very fast every year. So now I will move on to the Antarctic ice sheet, and I would like to start with the fact that the Antarctic ice sheet is also losing mass. There is no doubt about this. So the trend is very clear, even though the amount of ice loss is not as big as Greenland so far. And on the map as well, you can see where it's actually losing mass, and some few areas in blue where it's actually winning mass due to higher snowfalls. You see on the western part a dark, which is a place which is getting darker and darker, which is where the Thwaites glaciers and the Pyrenean glaciers are, which are prone to marine ice sheet instabilities. So this was just to make clear that right now it's already losing mass. And I would like to present why my PhD is important for the society, because we know it's losing mass, but what about the future? To do that, we are interested in how it evolved in the past, and I'm interested in the how it evolved during the last interglacial. So here you have two graphics, one which presents you the evolution of CO2 in the atmosphere during the 800,000 years, and the Antarctic temperature during this same period. So you see the oscillation between ice ages and interglacials, and the last interglacial is this one. And what you can see is that the temperature was a little bit higher, and it's this period lasted about 10,000 years. So it's actually the climate that we have now. So it's 1 degree warmer than the pre-industrial period, but for 10,000 years. So by looking at what happened at this period, we can think about what will happen if we stay in this 1 degree warming, or even further, potentially. So if we connect that to the sea level rise, here we have markers. So that's what I say, that so you have first the present time, where you have the CO2 before the 20th century, the CO2 evolution to the 2014, and you see that it's been so much high that it's actually higher, almost the same level as 3 million years ago. And in terms of sea level rise, you can see the contribution in different periods in the past. So the last interglacial, which is 125,000 years ago, is the second one. So that's the one I am interested in. So if we look in more details, we see that the Antarctic ice sheet is a major contributor to the sea level rise during this period. So my PhD is about modeling the Antarctic ice sheet coupled with the Earth system model. And this result will be compared with ice cores and marine sediment cores to make sure that all the results we have do make sense. So I show you already order of magnitudes of what we know from geological records the sea level rise was, but we don't know exactly from which part the sea level rise come from and which processes are triggering this sea level rise. And most importantly, if those processes are most likely to happen in the future, in the coming centuries or millennials. To finish, I would like to remember us that saving ice is also saving beauty, in the sense that on the right, you can see myself in the arms of my mother. I'm not even 1 year old, in front of a glaciers. And if I took this same picture with my, let's say, my children I could have in the future, I could not take the same one because this glacier has retreated and might completely disappear by the time I have actually children. And on the left hand side, it's actually where I live. It's in Amsterdam. And this place, even though it's not directly connected to the glaciers because of water resources, for instance, is directly connected to the cryosphere by the sea level rise. So we have a direct threat wherever we are, and we live in a beautiful world. And I think it's worth to remind us that it is the case, and we need to save it. It's just to bring us sort of fear is not always the leverage that we use. So maybe love is a good one to bring us to into actions. Thank you very much. And I will pass it on to Julie, who will present us about the Greenland ice sheet and Antarctica as well. Thank you.
I agree. Love is the answer. I like that. It's true. So Max talked about his research on Greenland, and I want to come back again to this audience and talk about what we know about these two ice sheets in the paleo world. And I would like to add something about the sea level. And I'll mention again, in case you were here earlier, something about this paper on the Paris Agreement. So we know today global mean sea level is rising at about 3.6 millimeters per year. And this has been accelerating. So we're seeing an acceleration of the accelerating sea level over centuries, particularly over the last 120 years. And this is well documented in the SROC report that came out just last year. And so as sea level rises, the question that was just brought up, well, how high was sea level in the past and where did it come from? What melted? It's a big question that I've been asking for a long time. So here I'm showing Andrea Dutton, who we hope will join online later this evening after the 6 o'clock talk. Andrea has been studying the last interglacial shoreline and looking at coral reefs of various kinds in various parts of the world. You can see this one's at 8 meters above sea level, roughly. And she's written compilations, and one of the figures that Max showed is from one of her papers. So she's working at looking at sea level. There are all kinds of people looking also at other kinds of sea level, like this paper that came out 2 years ago now, are cave deposits in Majorca. And in the cave is inland from the sea, but it's very close to the sea. And so for the stalactites and stalagmites to grow in the cave has to be empty, but there are these very unusual deposits that mark the level of sea level in the deposit, in these caves, fluctuated. And what these authors have done is worked out the relative tectonics, the local sea level, and all the various geophysical components. And they're able to show that in the Pliocene, 3 million years ago, sea level, when the temperatures were 2 to 3 degrees warmer in the Pliocene, sea level was anywhere from 16 to 17 meters above present. Okay. And in the warmest part of the Pliocene, when it was almost 4 degrees warmer than today, sea level as high as 23 meters. Now, this is at a time in the Pliocene when there wasn't any Greenland ice sheet yet. We didn't have northern hemisphere glaciation yet. So all this any fluctuation happening is coming from the Antarctic ice sheet. So huge changes in sea level during this time. And what's interesting, the same year, this paper came out from the Wanganui Basin. It's a sedimentological basin in New Zealand, first started by Tim Naish, who did his dissertation on this many years ago. And this is one of his graduate students who've looked at again, at the sedimentology of this and worked out the sea level story. And now this is from, on the left, the 3.3 million to 2.6 million, which is in the Pliocene again. And the red dots are deglaciation, the blue ones, so that's the warmer periods, and the blue ones are the glacials. And the point of this paper is that during this entire period, sea level was fluctuating back up and down about 13 meters. So again, we don't know exactly the relative position of the shoreline in this paper, but we know that Antarctica, this again has to be Antarctica ice, is fluctuating by 13 meters. So that's like 2 Greenland ice sheets worth of ice mass loss during various cycles in the Pliocene. So this is why it's really important to, when studies like this are going on all over the world, we look at where these shorelines occur. We have to think about relative local tectonics, worry about changes in just the flexure of the lithosphere, let's put it that way. And then we need to think about where the water came from, what melted at what time. And so we know today that Antarctica is contributing only a very small amount to sea level rise. It's this curve going down is showing mass loss over time. This is from 2002 to 2016. If you can't see it in the back, it's a little small print. And then, but the Greenland ice sheet is actually contributing more to relative sea level rise. And one of the obvious questions is, when will Antarctica take over in terms of being the dominant source? That's certainly of concern to us. But Antarctica is a big place. We have to remember that what's happening even on in my own country, what happens on the West Coast might be different than the East Coast, very different climatology. And we can't expect anything more different from the Antarctic ice sheet. Different parts of the ice sheet are going to respond more quickly than other parts of the ice sheet. So because we now understand the fact that which ice sheet melts and what's melting when can influence the magnitude of sea level around the world. This has actually been a difficult concept for a lot of the general public to understand, that in fact on the left-hand side is showing a map of the implications of 1 meter of of sea level rise coming from Greenland. And you can see from the bar here, the red colors are higher sea level, the blue colors are lower sea level. And you notice that around Greenland itself, even here in Scotland, with Greenland melts, sea level goes down. And the reason is the gravitational pull of the ice sheet itself on the sea level. There's actually a component of that, and it would redistribute mass into the areas that have the red bulges there, which have an accelerated or an accentuated sea level. In contrast, if the West Antarctic ice sheet melts, you see, again, sea level around the ice sheet drops when it melts, but elsewhere in the world, it increases. And where I am in the United States, I keep telling people 1 meter of sea level rise out of Antarctica really means 1.3 meters of sea level rise on the east coast of the United States. It's going to have about a 30% increase because of this geophysical difference. The Earth's surface is not flat, but bent by gravity. And so the distribution of the shorelines and their relative height correlated around gives us an idea of what melted for different interglacials. So we have kind of like a fingerprint, or maybe let's call it a barcode of where the ice came from which ice sheet. And these two ice sheets are so different. Greenland is basically a basin surrounded by mountains, and Antarctica, West Antarctica in particular, is a series of islands and below sea level, and East Antarctica has high mountains. So they're physically very different. The lower Antarctic ice sheet and West Antarctica can be called a marine-based ice sheet. It's based below sea level, whereas the Greenland ice sheet is basically filling a big basin. So they're physically very different, and we can imagine that they might respond different to climate. And so in both ice sheets, however, they both have this issue of what we call buttressing from the floating ice shelves that are coming off both Greenland and the Antarctic ice sheet. As ice flows to the sea, it starts to float, lift off the grounding line, and these ice shelves can be 300 or 400 meters thick. Okay, just of great thickness, and they are in fact pinned, as you can see here. They can be pinned by islands and areas around them that kind of hold them up, they're kind of pinned there against it. So these ice shelves act like a buttress against the flow of the ice, and they slow the ice down. And as we know, in both cases, both in Greenland and Antarctica, we're worried about the collapse of the ice shelves that are buttressing and holding back the fast flowing ice. So this process is going on both ice sheets. So despite their differences, there are some similarities in this process. So if the ice, the ice, as I said before, slows the movement of the ice back, and it creates this buttress. So it's just a visual thing. We all know what a cathedral is like. If we lose the buttresses, like the ice shelves, then there's fast flow. And there are many good examples of that. And the science is getting better in describing this. And I want to thank Rob DeCanto for sharing these slides for me. I did take off the equations, but I think the important point about thinking about the relationship between what we observe physically in these ice sheets and how we model it and describe it mathematically is always improving. And the science community is coming together and looking at how to parameterize how these ice sheets operate, and it's getting better and better. The last, AR5 did not have any of this kind of work in it. And so the new AR6 does have ice sheet instability built into it, which is a good thing. So here's some examples. The Larsen B ice shelf on the Antarctic Peninsula collapsed in a matter of 3 months. This picture is January of 2002, and you can see where the Crane Glacier is there. And it fell apart. It had a lot of water, fractures on the surface that were filled with water. That water helps to force the cracks open, called hydrofracking. And when this collapse occurred, this is March now, just a few months later, the Crane Glacier accelerated in its velocity by 3 times. So this was a big wake-up call. This is 2002. So, literally about 20 years ago that we started to have that kind of observation. And you can see the retreat of the grounding line being mapped in the Crane Glacier now that the ice shelf that buttresses it is gone. And as I said before, the International Polar Year about 10 years ago documented that 7 of the 10 ice shelves like this on the Antarctic Peninsula have all collapsed. They're all collapsed in the recent times. This same type of process is also happening in Greenland, in the Helheim Glacier, and also in Jakobshavn. Jakobshavn, many years ago, it wasn't that long ago, it was only moving at about 8 kilometers a year. It was considered a pretty fast-moving ice sheet. It is now moving over 14 kilometers per year. This slide's a little out of date. It's actually moving really fast because it's lost its buttress. So these are miniature, if you will, versions of what's happening in Antarctica. Now, these are 2 new papers that have recently come out trying to describe this buttressing. And I'm going to try to click the left one. There's an animation happening, and you can see that it looks to you like nothing's happening because it's actually trying to gradually start to come. And you start to see some fractures. If you look close, some fractures happening as the ice cliff starts to collapse. And you'll start to see this big slab come off. This is how we're trying to model, physically image what ice cliff instability looks like. Okay, and you see it taking off. This other animation from this other paper, it's a little faster. So now you see, again, how they parameterized that instability relatively quickly. So it's these types of models that help inform the climate-coupled ice sheet models in terms of trying to understand the future of these ice shelves. And why is this important? Well, we know that as the Earth warms, these ice shelves are likely to collapse. And in this paper by Tacanto and many, many members of the community, I think there's 13 or 14 authors on this paper, they showed that in the top panel is a 1 degree, 1.5 degrees. The middle panel is 2 degrees world increase, and the bottom is 3 degrees. And what this shows is that by the year 2100, Antarctica could, under 1.5 degrees, would contribute about 8 centimeters of sea level. That's about that much. And then at 2 degrees, it's only about 9 centimeters. So not too different. But by the time you get to 3 degrees, it's double, almost double. So there's a huge jump in the vulnerability and the contribution of melt from the Antarctic ice sheet once we get up to about 3 degrees. And again, 3 degrees is like a Pliocene world, like it was 3 million years ago if you extended that for a long period of time. So these are some images from this paper here showing with a box around the Thwaites Pine Island Glacier area, where the United States and the UK have a major program of observational science on top and underneath and around these ice sheets. So in this next image, hopefully, this image, this is by 2100. The contribution of sea level rise is about 15 centimeters. It varies between 8 and 27, you see. But this is the Pine Island and Thwaites Glacier starting to essentially bifurcate the West Antarctic ice sheet. So it's gutting it from the inside, in a sense, and at 3 degrees. And if we continue that out, by 2300 at 3 degrees, we're driving these ice sheets into a Pliocene world. That's Pliocene 3 million years ago was when the temperature was about 3 degrees above present. And by all estimates, probably didn't have much of a West Antarctic ice sheet and probably no Greenland ice sheet. So we can get an idea of at least the contributions and the timing of this ice loss. Now, the other point of this paper is also about how soon and how quickly we keep the CO2 low. And the later we wait to do it, the higher the consequences for how these ice sheets will respond. So this paper makes the assertion that if we don't start carbon dioxide reduction until 2060, there's a lower pathway that's still quite serious. But if we don't do anything by 2070, then the ice sheet could be in a runaway situation where the ice shelves are just going to respond catastrophically in a way that may be difficult for us to pull back from. So this is an important takeaway message from this paper. So on the left are shown some, again, the contributions from Antarctica, and these go out to 2300. Something to remember, we often use 2100 as a benchmark. Climate will keep changing after 2100, so we need to remember that. So this goes out to 2300, again, giving it 2 degrees, at least by then, about a 1 meter sea level rise. 3 degrees is about 1.5, and RCP 8.5 puts it up at almost 10 meters by 2300. So those numbers you see on the left shown here in the right on this diagram. So we're trying to get a better idea of, with this perfection in understanding the mechanisms of the ice shelves themselves and ice cliff instability, getting that physics correct in the models, we can make a better estimate of how much Antarctica, the big elephant in the room, is going to contribute to global sea level rise. So studies are still ongoing in terms of understanding this ice cliff instability. How fast could it collapse? Those animations give you a good idea about that. And so it's really, I think we should all be happy that at least these parts, this really critical piece of the science is included in the AR6 report. Greenland is also something we need to be concerned about. We know that, and we just heard about the mass losses from Greenland, that melting is accelerating, and particularly from year to year, but definitely accelerating. This is a reconstruction of what the ice sheet might look like by 2300, when we just saw what was happening to the Antarctic ice sheet, both contributing to sea level. And again, I think if you've been here through the day, this is, I think, the 4th time we've shown this, because it's such a beautiful animation showing you the portions of Greenland that have the largest rates of mass loss, particularly from melting. So if you can grab this and the animations from Antarctica from the NASA website, but you see that, and where is Jakobshavn? Helheim Glacier down here in these areas. And there's been a lot of studies going on in the Petermann Glacier in the upper northwest corner of Greenland. So Greenland, I said, is a basin. And we know that now a lot of these glaciers around Greenland, they actually head back into deeper terrain into the basin from the margin. So what this means is that all these little white dendritic pathways show you that as the ice retreats from those margins, there's nothing to stop it. It's going into deeper and deeper terrain. There's nothing that's going to help it. Despite even isostatic uplift, that's nothing that's going to stop it from retreating. So what we're seeing with Antarctica, we're also now seeing, because we have a much better idea from particularly work with NASA about what the bathymetry of Greenland looks like and how various parts of Greenland are more vulnerable to collapse into the interior of Greenland than perhaps we thought about before. So this paper came out, which I think is quite important to consider, suggesting under the different RCP scenarios how quickly we might lose the Greenland ice sheet. So as I said a little while ago, Greenland's future may be to turn green again. If in a RCP 8.5, it's only going to take about less than 1,000 years for us to get to that state. And we have evidence in the geologic past that this ice sheet can actually come and go quite frequently with only a very small change in temperature. And I think that's a really important take-home message. The top diagram here just shows you mainly ice extent and ice thickness. The bottom diagram shows you the changes in ice flow velocity with time. But even by 2100, sea level from this ice sheet could be as high as 33 centimeters, maybe as low, if we're lucky, of 5 centimeters. So this is my last slide. In the AR6 report, this diagram talks about the various scenarios for sea level. And you can see on the left diagram the projections for sea level by 2100. And you can see that with RCP 8.5 or SSP 8.5, we have about 1 meter of sea level rise. But what's important is that this version of the AR6 includes the question of ice sheet instability and has that dashed line, which is within the realm of possibility if we lose the ice shelves. So it can be not so bad, but it could be a lot worse if we lose these ice shelves. So consequently, this diagram on the left, which goes from 0 to 9 meters and shows you where sea level might be by 2300. So one scenario, if you follow this line, this lower one, this puts sea level out at 2300, somewhere between 2 meters and 7 meters. The blue line, the best case scenario, would put us somewhere between around, say, 0.5 meter to 3 meters, which would be great. But that dashed line up there goes up beyond 10 meters to accommodate that question of the ice sheet instability. So the tale of two ice sheets is simply this. They're very different ice sheets, different in size and configuration, but there are some similarities in the mechanisms that are happening in both ice sheets, particularly with the response of the glacial system to the loss of the ice shelves. And so this is a really important take-home message that the science community is getting better and better at quantifying the reconstructions. And we know it's important to policymakers, to coastal managers. You know, is it going to be 1 meter? Is it 1.5? That matters. That has huge cost implications for how we think about we manage our coastlines. And so the better we can get it quantified, the better we'll be off at planning for the future. We already have baked in at 1 degree possibly 6 to 9 meters of sea level. That's we're at 1.2 degrees now in global warming. That's what it was like 125,000 years ago when Andrea Dutton is measuring those shorelines, and others like her measuring those shorelines around the world. We know that that's what sea level was like at that temperature in a long-term scenario. So that's my last slide. I want to thank you very much, and I look forward to any questions you might have. And if I can't answer them, there's some other people in the room that probably can help us out. So thank you very much.
If anyone has some questions, they can just come up to the microphone here and ask them.
Thank you, Julie. I had just one question. You said at some point that with little temperature changes, the Greenland ice sheet might have gone and come. So my present day understanding is, as a glaciologist, that with a little warming, we start melting on the summit, which we have already started to some extent. But then you lower the ice sheet and it goes itself into warmer elevations. And in order to get it up again, you need much cooling and not just a little temperature. And I think that these much lower mountain chains in the east, they are not high enough to reach the elevation of the present day summit. They're much lower. So with a little temperature, you would not rise it. You need really a kind of an ice age cooling. Else you cannot build it up again. That is my understanding. Maybe you have another explanation.
No, I think you're right on there. If we just go back to this figure, I think it's right that the ice largely retreats into the eastern mountains. What ice is left is going to retreat into the eastern mountains. And yes, it's going to take a dramatic cooling, a lot, and allow that ice to come back. That's for sure. So this is pretty much why sea level rise is not reversible. It's not going to be reversible. We might talk about trying to bring back Arctic sea ice in the next 100 years. But the sea level rise is kind of permanent on human timescales. And this is why we really have to think now. This is why this is so urgent, because it's really difficult to grow this back. There's kind of, I think Rob DeConto would call it a hysteresis in the way the ice sheet collapses and then rebuilds. And it takes a much more dramatic cooling to bring it back. But we do know that even just a 1 degree warming 125,000 years ago took in at least 2 to 3 meters of sea level from Greenland. And I think Max showed that in one of his figures. And so if we go to 400,000 years ago, it was even warmer. Most people agree that a lot of Greenland disappeared. And so this right-hand side is maybe what Greenland looked like even 440,000 years ago. So the ice sheet history is still emerging, but we're getting an idea that this ice sheet is much more vulnerable than we thought before. Answer your question? Yes. Oh, go ahead.
So we can agree that the ice sheet is easy to remove, but it's very difficult to rebuild it again.
Perfect. Yes.
Hi there. Thank you so much for your presentation. I've been to quite a few presentations here at the Cryosphere Pavilion, and I find it very interesting. And I'm especially interested in sea level rise, but I'm wondering, I understand glacial and y'all think in terms glacially, but how do we get the average person to understand the seriousness? Like I see here 5 centimeters by 2100. It would be so easy for people to say, 5 centimeters and nothing. What's the big deal? I'm just wondering, how do you relay that in a way that drives home what that means.
Yeah, so I'll comment, and it looks like Max has a comment. So we can already see this happening, and I think the public is getting attention that now when there's a full moon, when we have a king tide, we're getting flooding in areas that weren't built to be flooded. Okay, so that means sea level is coming up in ways that people didn't expect it, well within the time that their houses have been built. And this just recently happened all up the Florida coast, up to even South Carolina. This is getting people's attention. But just think about, I know there's a really wonderful paper that came out showing the relative sea level rise in the New York area, and how the damage from Hurricane Sandy with a rising sea level, instead of being once in 1,000-year kind of event, is going to be something that happens every 100 years or even more frequently, because it'll become the normal type of sea level damage as sea level rises. And I think the most important, there are some practical points to make. Economic loss and costs of replacing that or protecting it in place, armoring it in place, which may be a bad idea. But, we're reminded that these coastal, where do we get our shipping? We're seeing shipping problems just even because of COVID and various issues. All of our shipping ports, they're all located at sea level. What's going to happen to those? They're going to be much more vulnerable. We even have a lot of oil refineries in Texas that would like to have walls built around them. I think we need to put it in economic costs. This is getting the attention of the economic communities. And then community loss, we need to think about county by county, city by city, it's getting the attention gradually. Not enough, I agree. Yeah, and Max wants to comment.
Yes, I wanted just to react on this question because I live in Netherlands. 25% of the country is under the sea level. But still, we don't see many consequences of the sea level rise that we already have today. But we already have 20 centimeters of sea level rise today. And this, we can see the consequences of this sea level rise already in Bangladesh, for instance. They have farmlands that they could not farm anymore because they have salty water in it now. And salty water is really bad for harvesting. And that is really important to say that it's not, we should not wait the maps to change to say sea level rise is really bad now. It's already affecting a lot of people, millions of people today. And I would like to come back to what she said, that the long-term sea level rise is here, and we have to act now to reach the most ambitious goals, which still triggers us 2 to 3 meters of sea level rise in 2,000 years, as you can see here. So it's already a lot. I was listening to a talk the other day, and Netherlands apparently is ready for 5 meters. So it means that if we are in the very, very most ambitious emissions, we are kind of okay, but we're not for more, even in Europe. And we should share. I mean, also the infrastructure, the economy should be shared with the people in need also already now.
Yeah, and don't underestimate the power of a picture. Just look at that poster back there from Climate Central. If you go onto their Surging Seas website, you can pick out your favorite place. You can raise sea level up and down. And this makes people blink. They were going to build a huge soccer stadium in Miami on some old brownfields, but the projections are it's going to be completely surrounded by water, in the next 50 years. So these kind of images get people's attention, particularly when you can say that, look, just think 2100, today's kids are going to, the children born to today's children, their grandkids are going to be living through this. It's here. And I think we need to put it in that human element into it, and go for the heart and the gut of what it means.
To comment on the my experience since I've been living in Amsterdam for 1 year, is that they built all the infrastructure called the Delta Works because they had a really bad flood in 1953. That was extremely bad. There was thousands of people dying, farmlands not exploitable anymore, and there was houses disappearing as well. So only one event was big enough to change the lives of thousands of people, even in Europe. And the whole thing is we should not wait to have those events happening anywhere else to actually act.
Yep.
Question. How much observational data is there for marine ice cliff instability?
How much observational data is there? Well, think about the fact that a lot of our remote sensing of the polar regions started in 1979. And so, and we've had more people on the ground looking at these ice sheets. So, it doesn't go back very far, but we've already seen some of these systems in Greenland go through this ice cliff instability. They're undergoing it now. And again, the examples we're seeing from the Antarctic Peninsula are really informing us to look at the other parts of the ice sheet. So I can't underestimate the power of the research coming out of the UK, US, the Thwaites and Pine Glacier story. That data is going to be coming out in the next couple of years, and it will really capstone a lot of the initial observations we have of these systems. So you're right, it doesn't go back very far, but if Shackleton could have seen the Antarctica back in the day the way we see it now, he would be quite amazed.
Okay, thank you. I think that's the end of this session. So thank you very much to both of our speakers.
Okay, thank you.